Now we move on to cyclins, cyclin-dependent kinases. For example, we have a cell and it needs to divide. And we have a cell which is dividing excessively. Now we have a problem here. Now, what will regulate this? What will stop the cell from dividing excessively? And what will induce the cell from dividing? So, we have categorized and we have identified some control factors in these cases. Cyclins and cyclin-dependent kinases, they induce progression through the cell cycle. And tumor suppressor genes, they suppress the cell cycle. Thus, the cell cannot divide. Thus, if there is the failure of tumor suppressor genes, we mainly see them in tumors and in some viruses. There are three major cell checkpoints. We see them at the end of G1, at the end of G2, and in metaphase of mitosis, as here marked in 1, 2, and 3. Now, what will lead to induction and what will stop them? As we have already said, cyclins and cyclin-dependent kinases, they will lead to induction. And tumor suppressor genes, they will suppress the cell cycle. And the cyclins and cyclin-dependent kinases, they combine together and form a variety of complexes. These complexes will help to drive the cell at various phases of mitosis and of cell cycle. Thus, cyclins and cyclin-dependent kinases, these will help to induce the cell cycle. But something should be present there in the cell which needs to stop this kind of thing. Because if there is no suppression of these things, the cell will divide uncontrollably. Thus, we have the tumor suppressor genes, like p53. It stops the progression of the cell. Thus, the cell has a machinery to regulate these complexes, and the cell stops dividing. Say we have a damage to DNA. Now, p53, it will inhibit the CDKs. Thus, the cell will not divide again. Now, cyclins may be of four types: D, E, B, and A. If we plot a concentration versus time graph in G1, S, G2, and M phase and see what is their concentration as the mitosis progresses, as the cell cycle progresses, we see an interesting graph. Now, for cells to go from G0 to G1, that is from senescent phase to a dividing phase, they need to have a particular amount of size. They need to have a particular amount of nutrition present, which will initiate this kind of thing. Once this amount of nutrition is present, it will initiate cyclin D. Thus, cyclin D, the prerequisites for cyclin D initiation is that it must have some nutrition. Now, what will happen after we have formed this holy grail, the cyclin D? It will bind with cyclin-dependent kinases, as we already said. What are those cells? What are those CDKs? They are CDK4 and CDK6. These CDK4 and CDK6, once we have the combination, they will suppress or inhibit retinoblastoma. Now, retinoblastoma, why is it important? Retinoblastoma holds E2F. Now, E2F is a protein which helps in the transcription of promitotic substances. Thus, the inhibition of retinoblastoma, it will lead to loosening of E2F, which is partially, not fully. Thus, it will lead to initiation of transcription, and some protein synthesis will happen and progression of cell cycle. Now, which proteins will be formed? The proteins which are helpful in the replication of the DNA, they will be transcribed. Also, cyclin E is transcribed during this by this E2F. Once E2F transcribes cyclin E, it reversibly binds to retinoblastoma again and fully loosens the E2F grip. So, to summarize till now, first we need nutrition. Nutrition will lead to initiation of cyclin D. Cyclin D will form complexes with CDK4 and CDK6. Once these complexes are formed, they will partially inhibit retinoblastoma. Partial inhibition of retinoblastoma will lead to formation of E2F. Now, this E2F will transcribe cyclin E, which will reversibly bind with retinoblastoma, inhibiting it fully. Also, this cyclin E, it degrades P27. Now, it is a tumor suppressor genes which inhibit cyclin D. Once you degrade P27, you are actually increasing cyclin D. And the E2F, which is now fully active, it will help in the formation of cyclin A. It will promote cyclin A. This cyclin A, it will form two complexes with CDK1 and CDK2, which will help in M phase and S phase. In M phase, it will later promote cyclin B. It is a mitotic cyclin which binds with CDK1, which forms mitosis promoting factors. Thus, the cell enters M phase and mitosis happens. Thus, to sum it up, we have cyclins, cyclin-dependent kinases, and tumor suppressor genes. The first two, they will mediate the cell cycle, and the third one, it will suppress. Once we have enough nutrition, the cell will go from G0 to G1 phase, and it will initiate cyclin D. This is the prerequisite for the cyclin D. It needs enough nutrition. Once we have the cyclin D, it complexes with CDK4 and CDK6. Once we have the CDK4 and CDK6, it will partially inhibit the retinoblastoma, one arm of the retinoblastoma which is holding E2F. Thus, some concentration of E2F, it will increase, and this will lead to activation of cyclin E. The cyclin E, it reversibly binds with the retinoblastoma, and it fully hits the retinoblastoma. Thus, E2F, it will increase greatly, and the E2F, it will lead to formation of cyclin A. Here, cyclin E, it degrades P27, which leads to more increase in concentration of cyclin D, because P27 actually inhibits cyclin D. Thus, we will move on to cyclin A again, which was increased by E2F, which was formed by a fully inhibition of the retinoblastoma. Cyclin A forms two complexes with CDK1 and CDK2 and drives M phase and S phase. Later, it forms a more stable cyclin, that is cyclin B. And this cyclin B, it will eventually lead to mitosis. Thus, this is the end of it. And one more point, what will lead to degradation of these cyclins? We need to stop the cyclins. There is something called ubiquitin. This ubiquitin, it leads to degradation of these cyclins. So these proteins, cyclins, they are marked, and thus they are degraded by ubiquitin protein ligase degradation. Hope it was helpful. Please subscribe and share.